Most people believe they know what pumpkin is. A seasonal vegetable, carved into lanterns, baked into pies. Simple, familiar, almost nostalgic. But inside one of America's largest food processing facilities, pumpkin is not treated like a vegetable. It is treated like a controlled industrial material, because the can sitting on a grocery shelf must behave the same way every single year. Same color, same density, same sweetness, same texture. No surprises. And achieving that level of consistency requires a system far more engineered than most consumers could ever imagine. We are talking about engineering. Fields planted with pumpkins bred not for beauty, but for molecular predictability. Mechanical harvest machines designed to move faster than human crews ever could. Thermal processes calibrated within degrees because a slight deviation can destroy thousands of pounds of product. And texture control so precise that even microscopic fibers are mechanically eliminated. But here is the part almost nobody realizes. Before this video ends, you will understand why many large bakeries and food professionals trust canned pumpkin more than fresh pumpkins themselves. Not because it is easier, because industrial control has quietly removed the single greatest risk in cooking: uncertainty. So today, we are stepping inside the full system, from whole pumpkins to perfectly engineered cans. And once you see the level of science, automation, and precision behind something so ordinary, you may never look at the inside of a pumpkin the same way again. Long before a single machine starts running, the process begins at the seed level. The pumpkins used for industrial puree are not the large decorative varieties seen outside homes every October. Most factories contract farmers to grow processing cultivars, dense, deeply colored, naturally sweet, and structurally consistent. Because inside a factory, variation is the enemy. Every pumpkin must cook at nearly the same rate, break down at the same temperature, deliver similar solids content. Even slight agricultural inconsistency can cascade into manufacturing instability. So growers monitor dry matter percentage, sugar development, flesh thickness, disease resistance, moisture levels. Harvest timing is calculated, not guessed. Too early and starches haven't converted. Too late and structural degradation begins.
But even perfectly grown pumpkins can still destroy a production schedule if they don't survive the harvest.
When maturity targets are reached, harvesting does not unfold slowly, it happens fast. Mechanical windrowers cut the pumpkins from their vines and align them into uniform rows across the field. Field loaders follow, lifting thousands of pounds per hour into transport trucks. Speed matters more than most people realize, because once detached from the vine, degradation has already begun. Some facilities require pumpkins to arrive within hours, not days. And before transport, many crops undergo curing, held in controlled warmth to toughen the rind and heal microabrasions. A damaged rind invites microbial intrusion, and microbes threaten shelf stability months later. Industrial food safety begins in the dirt, not inside the plant.
But when the first truck backs into the receiving bay, the factory still doesn't trust the pumpkins. They must pass inspection first.
Every incoming truck is sampled. Inspectors check for rot, insect damage, sunken flesh, mold, and irregular ripening. Even smell can trigger rejection, because one compromised load can contaminate thousands of future cans. Accepted pumpkins are weighed, logged, and scheduled into production, often within the same shift. Facilities try to minimize storage time. Fresh input increases flavor stability later. But here is something many never consider. Factories must synchronize farm deliveries with processing capacity almost perfectly. Too many pumpkins creates backlog and spoilage risk. Too few shuts down million-dollar equipment. This is agricultural logistics operating at manufacturing precision.
Now the pumpkins enter the line, but they are still carrying the entire field with them.
The first machines don't cut, they clean. Pumpkins travel through high-volume washing channels where rotating brushes, turbulent water, and food-safe sanitizers strip away soil, sand, field bacteria, and residual agrochemicals. Water filtration systems continuously remove debris to prevent cross-contamination. Because washing isn't about appearance, it is about microbial control. Every surface that touches the pumpkin from this point forward must remain within strict safety thresholds. But cleaning introduces a new variable, moisture, and excess water can interfere with thermal efficiency during cooking, so drainage conveyors immediately follow. A small detail with large downstream consequences.
Now the pumpkins are clean, but still structurally intact. That is about to change.
Whole pumpkins are too large and too unpredictable for efficient cooking, so size reduction becomes mandatory. Industrial cutters split them into segments using hardened stainless steel blades designed for continuous operation. Seeds and stringy interiors are mechanically separated early, preventing fibrous contamination later. And nothing is wasted. Seeds often enter parallel production streams for roasting or oil extraction. Meanwhile, pumpkin pieces are standardized for thermal penetration because heat moves predictably through uniform geometry. Irregular chunks create irregular cooking, and irregular cooking creates texture failure.
But the next step is where the pumpkin stops behaving like produce and starts behaving like a processed material.
The cut pumpkin moves into steam systems or continuous cookers. Here, heat performs multiple functions at once, softening cell walls, converting starches, stabilizing color, and reducing microbial load. Temperature bands are tightly controlled. Too low, and the flesh resists pureeing. Too high, and volatile flavor compounds degrade. Operators constantly monitor dwell time because cooking is not judged by appearance, it is judged by internal transformation. This is the moment the pumpkin transitions from agricultural product to manufacturable substrate.
But softness alone doesn't create the texture consumers trust. For that, mechanical force takes over.
Augers feed the softened pumpkin into industrial mills. High-torque systems shear the flesh into a continuous mass. At this stage, the material is not yet the puree found in cans. It is thicker, less refined, still carrying microscopic inconsistencies. Sensors begin measuring viscosity because flow behavior predicts filling performance later. Factories aren't just making food. Now they are engineering how that food will behave inside machines. Yet even after milling, something invisible still threatens the final product.
Fiber can ruin the perfect mouthfeel, and the next step is where it is eliminated.
The puree is forced through screens and finishing units that remove remaining particles, skin fragments, strands, dense tissue, anything that could disrupt mouthfeel. Most consumers would never consciously detect these defects, but they would feel them. And in industrial food, perception defines quality. Now the puree becomes uniform enough to standardize. And this is where one of the most powerful, yet least discussed factory practices begins. Because natural pumpkins never taste identical, but the cans must. Batches are tested for Brix, or sugar concentration, pH, color metrics, moisture ratio. If natural variation appears,
Processors blend batches to restore specification targets, not altering the pumpkin, balancing it. This is why a pie baked this year tastes like the one baked 5 years ago. Consistency is not accidental, it is manufactured.
But even perfectly standardized puree can still spoil unless one final biological threat is controlled.
Before packaging, the puree undergoes controlled heating designed to destroy pathogenic organisms. This step is calibrated carefully to preserve flavor while ensuring commercial sterility. Because once sealed, there is no second chance. Food safety is built into the timeline, not inspected afterward. This process ensures commercial sterility without compromising quality.
Now comes the moment where fresh product becomes shelf-stable.
Empty cans arrive sterilized. Fill heads dispense exact volumes within tight tolerances. Underfilling violates labeling law. Overfilling disrupts thermal processing later. Seaming machines hermetically seal each container, forming an oxygen barrier critical for long-term stability. Modern lines inspect seams automatically. Defects are rejected instantly. Most consumers never consider the engineering hidden inside a lid.
But the cans still aren't safe for storage, not yet.
Sealed cans enter massive pressure vessels called retorts. Inside, high heat, elevated pressure, precisely timed cycles. This environment destroys spores capable of surviving normal cooking. Only after retorting does the product achieve true shelf stability. This is why a can may last years unopened. It is not preservation by luck, it is preservation by thermodynamics and microbiology.
Now the pumpkin is safe, but the factory still isn't finished with it.
Rapid cooling prevents overcooking and protects texture. Each can receives a batch code linking it to production data down to the minute. If an issue ever emerges, manufacturers can trace it instantly. Transparency is engineered into the system, not added later. And finally, the pumpkins that began in open fields are prepared for national distribution. Robotic arms stack finished cans with repeatable precision. Pallet patterns are optimized for transport stability. Warehouses manage rotation schedules so older inventory ships first. From here, trucks disperse the product across thousands of miles. Weeks from now, these cans will sit quietly on grocery shelves, indistinguishable from one another, exactly as intended. At the beginning of this video, we opened a question. Why do many professionals trust canned pumpkin more than fresh? Now the answer is clear. Fresh pumpkins carry natural variability, but inside a factory, variability is systematically removed. Controlled agriculture, measured cooking, engineered texture, verified safety. Uncertainty eliminated step by step. What appears simple is actually one of the most controlled vegetable products in modern food manufacturing. So, the next time you open a can of pumpkin, understand what you are really holding. Not just harvested produce, but the outcome of synchronized agriculture, food science, thermal engineering, microbiological protection, and precision manufacturing. A system designed to remove uncertainty, one controlled step at a time.
If this level of engineering changed the way you see something as ordinary as pumpkin, subscribe and continue exploring the industrial systems most people never stop to question.